In any modern factory, you'll see a perfectly synchronized ballet of robotic arms handling complex assembly tasks. But this motion doesn't happen by magic. Before any of that machinery can run, the brain of the operation, the programmable logic controller, or PLC, needs to be physically wired to the outside world. To show you how that is done, we are going to use this trainer board, which features an Allen Bradley MicroLogix 1000 PLC. The very first step is also the first place where beginners make a critical mistake. You must perfectly match incoming power lines to the specific electrical requirements of the PLC model. This diagram shows the exact power input locations. Look closely at this label right here. It requires 85 to 264 volts of AC power at terminals L1 and L2. Wiring a DC power supply to these AC terminals will instantly destroy the board. Once you provide that correct main power, the PLC's internal processor wakes up and begins executing a continuous operating cycle. This repeating loop has 4 distinct stages. First, the input scan checks the state of connected devices. Next, the program scan executes your logic. Then the output scan energizes field hardware. Finally, housekeeping handles communication and internal diagnostics. Without establishing those precise physical power connections first, the controller cannot initiate this loop, and any software logic you write will sit completely idle. Now that the controller has power, it needs a way to monitor the environment. We do this by connecting discrete input field devices, like pressure switches or toggles, which serve as the physical senses for the system. Here you can see how these connections are organized. Wires run from the external toggle switches on the left, pass through this plastic terminal block, and then feed directly into the top input section of the PLC. Notice that every electrically common conductor shares the exact same wire number. This is a strict rule in control wiring to ensure the circuit remains readable and safe to troubleshoot later. Next, take the wire from your primary discrete input device and connect it to a specifically numbered input terminal. On our board, we are connecting this green wire to the terminal designated as Input 2. What happens in the real world is that when the physical switch changes states, like a pressure switch closing once a tank hits 50 psi, it allows electrical current to flow directly into that assigned terminal. Wiring an input simply establishes a clean physical pathway to deliver a true or false electrical voltage to one exact pin on the processor. Once the PLC reads that incoming voltage, it needs a way to react. That brings us to the action side of the loop, wiring actuators to the output terminals. Inside the controller, these output terminals act as internal gates. When commanded, they close to provide switched power out to the field, completing the circuit for external devices. This schematic demonstrates how we route a wire directly from a designated output terminal, in this case terminal O1 on the bottom row, out to a physical alarm lamp, and then tie it back to a common ground. The PLC will physically energize or de-energize this specific terminal, turning the lamp on or off, based purely on the instructions it calculates during the program scan stage. Before PLCs existed, achieving this required routing power through a chaotic array of physical electromechanical relays. If a single sequence in the factory needed to change, technicians had to manually unscrew and rewire the entire panel. Today, correctly wiring these output terminals gives the PLC all the pathways it needs. It is the only way to translate the invisible decisions made in software into actual physical work. Now we have a perfectly wired hardware loop, but the processor still doesn't know what to do with it. We bridge the physical wires and the software logic using a process called I/O mapping. This is where a lot of beginners get stuck. You can write flawless code, but if your software is looking at one virtual memory address while your physical switch is accidentally wired to another, the system simply won't work. Looking at this ladder logic interface, you can see how we align them. On the top rung, we assign this virtual contact the label pressure switch and map it specifically to address I0/2, perfectly matching the hardware input terminal we just wired. In the logic software, this element represents our physical switch. When the physical switch is closed, the software reads the voltage and treats this virtual instruction as activated. This instruction table details what that looks like. The software uses this parallel line symbol, called a normally open contact. It mimics the behavior of a physical contact and only passes the signal forward when its related bit is true. The final step ensures our software's output instruction is mapped precisely to our physical actuator's terminal. Down on the second rung, we take the software output coil, which represents our alarm lamp, and assign it exactly to address O:0/1. This process of I/O mapping is the ultimate bridge. A perfect physical circuit and perfect software logic will both fail completely if they do not share the exact same address map. Let's test the complete system. We manually flip the physical toggle switch, and instantly the mapped output lamp turns on. Here's what just happened in a fraction of a second. The incoming power enabled the CPU. The physical input was read. The mapped software processed the data. The mapped output triggered the lamp. If the factory rules ever need to change, you don't touch a single physical wire. You simply rewrite the virtual logic inside the PLC. By mastering this basic hardware to software translation, you create the stable foundation needed to safely control massive, complex industrial environments.